for love to be realized. I'll send her my heart covered as a gift, and hope that you'll take it into her side.
Hello everyone, this is József Nagy here, and in this video I will show you how to run your first simulation in OpenFOAM. I will do it step by step and I will explain every step in detail. Here you see the finished results. We will solve a two-dimensional flow in an elbow. Here you see the velocity magnitude, the pressure divided by the density, and I will explain how you can save these pictures and how you can write out diagrams. The goals of this tutorial are the following. I want to show you how the case setup is built up, how you can check the initial values and maybe even change them, how you can import a mesh externally and how you check the boundaries if they are set up correctly, and then in the end I will show you how to simulate 75 seconds of a flow in a two-dimensional elbow geometry on 3 different meshes, on a tree mesh, a quad mesh, and we will refine this quad mesh. And I will show you how to post-process the results. For that we will use the Icofoam solver in OpenFOAM. The official description is that it is a transient solver for incompressible laminar flow of Newtonian fluids. So this means that this solver is incompressible, it is a transient solver, it only works for laminar flows and only for Newtonian fluids, it is a single phase solver, and it is an isothermal solver. Now, as for the theory, incompressibility means that the continuity equation reduces to this simple equation where the divergence of the velocity is 0, and in the momentum equations you can divide by the density, and what you end up with is this. In the pressure gradient term you divide by the density, and in the diffusion term you have the kinematic viscosity instead of the dynamic viscosity. Transient behavior can be seen here in the momentum equations. You have a partial time derivative. You would also have a partial time derivative in the continuity equation, but since we are assuming an incompressible fluid, the density does not change over time. Laminar means that we do not have an additional treatment of turbulent phenomena. Newtonian fluids means that here in the diffusion term we only have one constant value for the viscosity that is constant over time and in the entire domain. Single phase means that we do not have an additional treatment of, for example, multi-phase phenomena. Isothermal means that we do not have an energy equation here. And I want to point out that the pressure P is not really the pressure, but rather the pressure divided by the density. So if we see later on the simulation the value of P, or I say pressure, then we have to know that we mean actually the pressure divided by the density. This is important. And the continuity equation and the momentum equations are not solved consecutively or separately, but rather are combined into the so-called piezo loop. Okay, let's just jump into the simulations. For that I will open up a Nautilus here, and my installation is in my home. Here you see OpenFOAM 2.3. Your installation might be in /opt, and here like I have the version 2.2, and then you take the tutorials from here. In order to operate in /opt you have to be root. So either you do the tutorials as root, or you copy this folder into your home. But what I will do, I will go into my installation here in my home, and then I will go into my tutorial folder. Here, so home, OpenFOAM 2.3 tutorials. We are dealing with an incompressible solver called IcoFoam, and here we have our tutorial case. Now, it is a very good idea to have a base case that you set up and then make copies of that base case. Now, this is what I'm going to do. So I will click on elbow, Ctrl C and Ctrl V, and I will rename this elbow to elbow tree, because we will use a tree mesh. And I will do a second case and a third case. And I will call this elbow underscore quad. No, quad. Yes, and then I will name it this. So elbow underscore quad underscore refined like this. Good. Before I do anything else, this elbow tutorial comes with a mesh file, which is a tree mesh. But here in the quad cases, we do not want to use this tree mesh file. So I will delete this here, and also in the refined case, delete. And here I have another mesh file, which includes the information of a quad mesh. You will get this file, so don't worry. I copy this, Ctrl C, and I will copy this into the quad case and the refined quad case. Good, so now we set up more or less the cases. Let's just go into the tutorials, the cases themselves. This is what an actual OpenFOAM case looks like. Ignore these two scripts. We could just delete them because we will not use them. And then we have a 0 folder, a constant folder, and a system folder. In 0, you have your initial conditions. You see P and U. P is the pressure. But again, I want to remind you that P is not really the pressure, but the pressure divided by the density. So in this text file, you have a header and then the dimensions of your value of P. And here you see the exponents of your 7 SI units. So the first one is the exponent of kilograms, so kilogram to the power of 0, so this is 1. Then meters to the power of 2, seconds to the power of -2, and then the rest of the SI units, but they should not concern us at this moment. So what we have is a unit of meter to the power of 2 and second to the power of -2. Now this is not the dimension of pressure, this is not Pascal, but it is the dimension of pressure divided by density again. Then what we are doing here, we are initializing our pressure with 0 in our entire domain. And then we have our boundary fields. We call these boundaries ball 4, velocity inlet 5, velocity inlet 6, pressure outlet 7, wall 8, and front and back planes. Now what does that mean? We set the boundary conditions, for example, on wall 4 to be 0 gradient, which is a von Neumann boundary condition. The same is true for the velocity inlet 5 and the velocity inlet 6. And on the pressure outlet 7, we fix our pressure to be 0, which means that here we are fixing the pressure to the atmospheric pressure. And on the wall, we have again 0 gradient. And then we have an OpenFOAM specific boundary condition called empty for the front and back planes. And I will come to that a little bit later. I will show you what this means. Again, then the velocity. Here you see again the header. And then the dimensions, meter to the power of 1 and second to the power of -1. So this is meter divided by second. And then we are initializing not a scalar value, but rather a vector, because the velocity is a vector, and we are initializing the velocity to be 0, 0, 0 in our entire domain, at the beginning at least, and then we are fixing the velocity to be 0, 0, 0 on the wall 4, which is the no-slip boundary condition. We do the same for wall 8, and then we are fixing the velocity at the velocity inlet 5 to be 1, 0, 0, so 1 meters per second in the x direction, and then on the velocity inlet 6 we are fixing the velocity to be 3 in the y direction. On the pressure outlet we are using a von Neumann boundary condition, and again we have our empty boundary condition. Good. Now let's get out of 0 and enter constant. What do you find in constant? Here you have a folder called Polymesh and a dictionary, a text file called transport properties, and here you can set one value, new, and this is the kinematic viscosity. Now we could change this value, but I will leave it as it is. Usually in a more sophisticated solver you can set multiple things here, but this is a very simple solver, so I will just leave this. And in Polymesh we will have our mesh data. We did not create a mesh up until now, we will do it a little bit later, but here in Polymesh we will have the mesh files. In systems you find your controls for the simulations, like you find your controls in constant that are constant over the simulation. Here you find the controls for the simulation itself. Normally you have these 3 dictionaries here, forget this. In control dict you find settings like the start time, then where to start from. Latest time means that if you start your simulation and you stop, for example, after 10 seconds, and you want to continue on from 10 seconds, then you say start from latest time and OpenFOAM will start from 10. If we would use a different setting, for example start time, then OpenFOAM would ignore that we already calculated 10 seconds and OpenFOAM would start at 0 again. So I will leave latest time here, and I want to simulate until 75 seconds. I will use the delta t of 0.05, and I will use a write control and a write interval. This means that OpenFOAM will save after 20 time steps, which means OpenFOAM will save after 1, 2, 3, 4, 5, 6 and so on seconds until 75. So this is what I want. I save this, and now let's just take a look at the other 2 dictionaries. Here you specify your discretization schemes. I will come to that in a later tutorial. And in FV solutions we are setting the matrix solvers and the tolerances and 2 values, n correctors and n non-orthogonal correctors. In order to understand what these mean, I will go to the source code. So you find your source code in OpenFOAM, OpenFOAM 2.3 or the version you are using, in applications, solvers, and then incompressible, icofoam, and here is the source code. You have createfields.h and icofoam.c. I open up icofoam.c. You have a header, and then you include a couple of header files. You create the time, the mesh, and you include create fields, which is this file here. In create fields you read in your viscosity from transport properties from here. Then you read in your P file, your pressure, but actually this is the pressure divided by the density. Then you are reading in your velocity, which we set to be 0, 0, 0, and we fixed the values on the walls and on the inlets. and then we are creating the flux, and then we are going in to the time looping. And here you see we set up a vector matrix with the partial time derivative, with the divergence term and the Laplacian term. So this is the convection term and the diffusion term. And then we solve this vector matrix with the pressure gradient term. So we are solving it, and then we are entering two for loops, the inner loop and the outer loop. And these two values, these n correctors and the n non-orthogonal correctors, specify the number of iterations. So what we are doing here, we are entering the first loop and the second loop. There we are solving the pressure equation of the piezo loop twice, and then we are going out of the inner loop. Then we update our velocity with the new pressure value. Then we again enter. We do the second iteration of the outer loop. We enter the inner loop. We are calculating the pressure equation again with the updated velocity twice, and then we update the velocity again. Yes, and then the next time step. So this is what the solver looks like, what we are doing in the solver. I will go back to the tutorial case. It was in incompressible icofoam, and elbow 3 is where we set the values. Yes, elbow 3, 75 seconds. So I showed you now everything. So actually we can just jump into the simulation. For that I open up a terminal. I could click here the terminal, or you just press Ctrl-Alt-T and then you have your terminal. Now I have to navigate into the folder of the tutorial. You can do that in Ubuntu or in Linux with the command cd, change directory, and then you type in the path. So OpenFOAM, but instead of typing in OpenFOAM, I just type in cd space op, and then I press tab, and then it will fill in the name of the folder. Then the next folder inside OpenFOAM, again op, and then OpenFOAM 2.3, and then in 2 tutorials, and then EIC, no, IN, incompressible, and now IC, icofoam. And then let's check icofoam elbow underscore 3, elbow underscore 3. Now we are in this folder, in elbow underscore 3. With the command ls, I can list the contents of the folder. So we have again 0, constant, elbow, and system. Now we checked the initial values in 0, p and u. We could have changed something, but we didn't. Now I want to import the mesh from this mesh file called elbow.msh. You can do that with the command fluent mesh to foam, and then space, and then the mesh file. Forget this command, we will use this command in this first tutorial, but in later tutorials we will use a different way to create our meshes, but for the first simulation this is good enough. So fluent mesh to foam elbow.msh, press enter, and now we have our mesh. Let's check, do we? We are going into constant and polymesh, and indeed now we have our mesh files. I want to open up this boundary file. This is important because here you store your boundaries. If you remember back, here in P and U we set our boundary conditions, and we had specific names for our boundaries. That came with the tutorial in OpenFOAM, but it is very important that we have the same names in this boundary file and in our P and U files. So you see we have wall 4, velocity inlet 5, velocity inlet 6, pressure outlet 7, and wall 8 and front and back planes. And we are giving our wall for the type wall, velocity inlet is patch, velocity inlet is patch, pressure outlet is also patch, wall is wall, and front and back planes are empty. So important is that the names match here and here, and now I come to this part, to the empty part. For that I want to show you the geometry, and for that I will use ParaView. Now how to open your case in ParaView? You type in ParaView space and this will open up ParaView. Let's wait until ParaView loads. Good, now we have to open the case. For that, you go here to open, and now we are in our case folder elbow_3. And what do? You go into System, then you go down here to All Files. You click your control-dict, OK, and then you choose here OpenFOAM, OK, and now you can click Apply, and now you have the geometry. So you have this two-dimensional geometry, elbow geometry. Let's take a look what's happening here. At first, let me show you the mesh. This geometry is made up by triangles. This is the reason why I called this case elbow_3. So the cells are triangular cells, and it is a two-dimensional case. In OpenFOAM, you have to always create a three-dimensional mesh, and in the direction where you do not want to solve the equations, you have to put one cell. Like here in the Z direction, the geometry only consists of one cell. So if I show you now these front and back planes that we define to be empty in the boundary file here, and also in P and U here, these are the front and back planes, and these planes define the direction in which OpenFOAM should not solve the equations. Okay? And with this, OpenFOAM will only solve the equations in the X and in the Y direction. Now, as for the other boundaries, let's go, for example, velocity inlet 5 is this here, and velocity inlet 6 is this here. So maybe if okay, and then let's just continue. Wall 4 is this wall, and wall 8 is this wall, and then the pressure outlet is up here. So if I go back to my velocity, on velocity inlet 5 we set the velocity to be 1. So velocity inlet 5, this is this here the velocity is 1 in the X direction, and this is velocity inlet 6, and here the velocity is 3 in the Y direction. So let me just bring up the mesh itself. Good, so this is what the geometry looks like. And now I will quit ParaView. We set up the case as we wanted. We imported the mesh. Now we can just start the simulation. For that I will type in icofoam and press enter. And now the simulation is running. We wait until it stops. And there you go. The simulation went until 75 seconds. Here The clock time was 7 seconds, so it was a rather fast simulation. And what do we see here in the output? We have the Kuro number. If you know what this means, then you know that it has to be smaller than 1. And indeed, the maximum Kuro number is 0.5. I will come to that in a later tutorial. And then it says solving for ux and uy. This means that the Navier-Stokes equations, if I go back to here, so this is this solving, the momentum equations are being solved in the x and the y direction. This is exactly what we want. We do not want to solve the z in the z direction. And then we are entering the outer loop and the inner loop, and then we are making 3 iterations. Here we set for the inner loop 2 iterations, and I told you that we are doing 2 iterations, but actually I was wrong. We are doing 3 because you always do at least 1 iteration, and this number is the number of additional iterations. And this n-core is then the actual number of outer iterations. And you see the first outer iteration and the second outer iteration. Good. Now let's take a look at our results. So again, I open up ParaView. Let's wait until ParaView loads again. Good, now let's just open up. And now you see that here we have the results for each second. If I type ls here, you see again, you have 75 results. I go into 75, and here what do we have? We have P, phi, and U. P is the pressure divided by density, U is the velocity after 75 seconds, and phi is the flux through the phases of your cells. But I will come to phi in a later tutorial. Let's just take a look at P. And I will not open up P here in gedit. I could, but I will show you a different possibility. I will use, for example, the editor nano, which opens up a text file in the terminal. So nano P, enter, and now you don't have an external window, but the text file is opened up in the terminal, and you can modify your file in the terminal, but you cannot click around with your mouse. You have to use the cursor. And what you see here, you see again the header file, the dimensions, and here you do not have a uniform value for the internal field, but rather you have a list of scalars, and each entry in this list corresponds to the value in one single cell. So here we have 918 cells and 918 values. And in the bottom you have the boundary conditions. You can exit with the command Control X. Same is true for the velocity. The velocity has also 918 entries, but here you have vectors. And then the boundary conditions. Good, so now let's just open up this in ParaView. Again, system, and then all files, control dict, and OpenFOAM. Okay, apply. Again, we have our geometry. And now let's take a look at the velocity. With this you can toggle the legend here. With this you can rescale the data range, and I will come to that a little bit later. So what you can do, you can go to the next time step, to the next result, and then browse through your results, or For smaller cases, you can just play. And this is what an animation would look like. Okay, but I will stop that. I will immediately jump to the last time step, to 75. I will rescale. And what you see, you have here a velocity of more or less 1 meters per second in the x direction, and you have more or less 3 meters per second in the y direction here, and here you have a mixing of the velocity. And here you see that you have these triangles, and these triangles are actually created by your mesh. So you see your mesh in your results, and that's not very good. You should avoid that. If I show you the pressure, here you see the pressure, but also with the pressure you can more or less see the mesh, and that's not very good. So what can you do? You can try another mesh, and for that I will exit the elbow underscore tree case, and I will enter the elbow underscore quad case. Now for this we have to change a couple of things. In 0 we have the same files, and we did not change anything here, so I can exit here. In constant we have the transfer properties again, and in polymesh we do not have anything yet because we did not create a mesh here, only in the elbow underscore tree case. And in system I have to change the end time, and now I will not open up the control dict here in elbow underscore tree and system, but I will open up this with the nano editor now. Let's just open up nano control dict, enter, and now I can change the end time value here to 75. I will use the same delta t and the same right control and same right interval. I want to mention here that you can save in nano with the command Ctrl O. I import the mesh again. Before we imported it with the command fluent mesh to foam and then elbow underscore msh, but now we want to import this mesh file which contains the information of a quad mesh. This is what I copied here into this folder at the beginning of this tutorial, so I type in elbow underscore quad.msh, I press enter, and now we have our mesh imported. And at this point now I can start the simulation, but before I do this I conclude the first part of this tutorial. I hope you enjoyed it and that you learned something. I thank you for watching, and I hope to see you in the second part of this tutorial.